Hello, this is Brady O'Leary, and we are here for our third module or third installment of our masterclass series. I'm Brady. I'm your host for the day. I'm one of the co-founders of Triple Point. I've been doing nothing but wastewater lagoons since I started my professional career about 15 years ago. And I'd like to think that I've got a little bit of experience around it, and I'll talk to you a little bit more about that in a second. So we today are going to be talking about lagoon hydraulics. And when I was first given this topic, I thought to myself, how am I going to talk for an hour about lagoon hydraulics? It's like pipe comes in, pipe goes out, water sits for a little bit of time, right? Anybody have any questions? And I started working on it and thinking about it a little bit more and more. And this is actually a very, very rich topic with a lot of different considerations. Hydraulics it's one of the primary drivers of treatment in a wastewater lagoon. It's one of the most important things that helps your lagoon either work well or not work the way that it was designed. So we're going to be talking about hydraulics, why it's important, how to optimize the design of your lagoon system or the operation of your lagoon system, or potentially how to troubleshoot some issues around hydraulics. So let's jump in. Like I said, this is the third installment of our masterclass. You've already hopefully viewed our masterclass presentations on lagoon process and biosolids. Future masterclasses will include algae, nutrients, data, troubleshooting, analysis, with the idea being that if you go through this entire masterclass, you're going to have a very good foundational understanding of wastewater lagoons, their operation, and their design. If you're looking for more content outside of this masterclass, we do have what we call our Lagoon University, and this is where we place our webinars and trainings on a whole host of different topics. And you're going to get some more nuanced topics here. This isn't necessarily masterclass material. Some could be overlap. Some is more detailed or specific. For example, and we have a presentation on specifically lagoon aeration and specifically wastewater lagoon screening. You'll find probably something here that you're going to be interested in if you work with wastewater lagoons at all. All of these are designed to be primarily educational, and it's a great resource we found for the operators we work with and the engineers that we work with. So, agenda for today. We're going to be talking lagoon hydraulics, and this is me over here on the right, just to prove that I do work in wastewater lagoon. This is me cleaning off some rags on an aerator. I can tell you when that aerator started, it looked like Chewbacca. This is where I learned wastewater screening is very important. I didn't have to watch a Lagoon University webinar. I just got out there and had to rip all these off for the better part of a day. So wastewater screening, very important. Like I said, I've worked in, on, around lagoons, have not fallen in yet, but I'm sure that wastewater baptism is in my future at some point. So for the conversation today, we're going to be talking about the basics of wastewater lagoon hydraulics, a couple of critical concepts. The first one being plug flow. We'll talk about why hydraulics matter, HRT, short circuiting. Short circuiting is a big one, the problems that it causes, what it is, how to diagnose it, how to remedy it. We'll talk about mixing, influent and effluent design, baffles, how different field conditions affect or are interrelated with hydraulics, and then a couple of other little bolt-on bits of information. Little lagoons do it better shout out actually for later, which is a pretty fun one, and a couple of quick tips related to hydraulics. So what is hydraulics? It's a very ambiguous term. Hydraulics is a branch of science concerned with the conveyance of liquids, especially as a source of mechanical force or control. So the idea here is we have a wastewater lagoon, it's full of water, and it's not just sitting there. It's not stagnant, the water is moving. So we need to get a sense of why that water is moving. Do we move it or does it produce a mechanical force? It does. It'll actually push or move along the process as the water forces the water in front of it down through the system through gravity. And there's also a relationship with control. We want to control the hydraulics in these wastewater lagoons such that we get the water and the bacteria to do what we want it to do at any given point. So there's a quote here from Middlebrooks. He's one of the classic researchers of wastewater lagoons, probably one of the last ones that spent a lot of time researching wastewater lagoons back in 2000, and he said that short circuiting is the greatest deterrent to successful pond performance or successful lagoon performance, barring any toxic effects, right? If there's no toxicity, the next biggest problem in a wastewater lagoon system is going to be short circuiting. So we'll be spending a lot of time talking about that today. And he continued by saying, the importance of hydraulic design of a pond system cannot be overlooked. It's one of the most important things you can look at when working with a wastewater lagoon system. So we're gonna start 30,000 foot view. I know for 99% of you, you understand this, but I wanna get a baseline of information down and build from there. So we all know that a wastewater lagoon is an earthen-lined basin. It might have clay, it might have earth, and then a HDPE liner, but very, very rarely, and I'm talking like 1 in 1,000, do we see a concrete-lined basin. We're typically using the earth. Wastewater lagoon systems generally are multi-cell, unless it's a interesting or a more uncommon use case, like a storage pond or an EQ basin. If it's used for process, it's almost always going to be multi-cell, either one large basin split up with baffles or multiple disparate basins daisy-chained together. Overall, the lagoon systems are meant to hold around 20 to 40 days of water. We'll talk about why in a little bit. Some lagoon systems hold much lower than that, and many lagoon systems could hold a lot higher than that. And we'll again discuss those considerations a little bit later. And almost all lagoon systems are gravity flow. It would be really silly to pay to pump water to get it into a lagoon system, and then to have to pay to pump water from lagoon to lagoon to lagoon. I'm not sure I've ever seen that, ever. So what we're dealing with primarily is the movement of water through gravity within the lagoon system. How does the water hydraulically get there? Again, I know 99% of you already know this, but let's just cover the basics. We use primarily the same thing, gravity. You'll find that most lagoon systems are at the lowest point or one of the lower points in a town or municipality, oftentimes down by a river, and usually the water is at one of the lower points in the town. And different wastewater discharges, whether it's municipal homes, will discharge their water and will gravity flow down towards the lagoon system, or industrial plants will discharge and will gravity flow down towards the lagoon system. If at any point the wastewater needs to go uphill, the municipality will use a pump station and a force main. And a force main is just a fancy word for a pressurized pipe, where this pump pressurizes it and pushes water up and over a hill or potentially multiple hills to an eventual wastewater treatment lagoon. One big concept that's important to understand with the wastewater lagoon system is that it is a plug flow system. It is not a bucket that you fill, you let sit for 20 or 40 days and you come back to it. That's not how most lagoons are operated. That's more storage fill. In those cases, if you're filling the lagoon system and you don't have an expected change, you don't want any treatment to occur, you're not planning on treatment to occur, and what you're trying to do is just hang on to the water for some future use, whether that's irrigation or disposal or discharge at some other point. That's not how lagoons are operated. It's not a batch, you fill the bucket and you're done. Lagoons are plug flow, which means you have water coming in, and that water, we'll say this ring of water starts, see this right here? That ring of water starts right here, and we put it in on day one. And then it moves through the system, that same rough batch of water moves through the system across the continuum as time goes on. And along that process, this wafer is moving through the lagoon system, say, or just like it's moving through this pipe, it has a DX or a change of concentration. As the water moves through the lagoon system, we're expecting that water to change across the continuum, and that's wastewater lagoon process in a nutshell. So, like I said, the water changes across the continuum. It is intended to follow a process. It's supposed to start right here and end up at the other end of the lagoon system. If we were to start in the middle or to bypass parts of the anticipated process, we're not going to get the outcomes that we're looking for. So that's an important thing to note here, especially when we start talking about short circuiting. If we sidestep this plug flow process that's designed around, you're going to have problems. So let's talk about some basics with wastewater lagoon systems, the ins and the outs. Like I said, we're gravity flow, we're plug flow. And when the water comes into the lagoon system, generally it's moved around through a series of transfer pipes. So no, we don't want that. So you have these influent pipes here. The water's coming in split evenly amongst these three, and this is just a random sample. This arrangement may be different at some other lagoon system. But the water comes in here, and then it travels down through this transfer pipe into this lagoon, through this transfer pipe into this lagoon, and through this transfer pipe to the effluent. These pipes are generally sized to minimize head loss. You don't want to see meaningful head loss across these pipes. And then we have multiple flow regimes that we're going to talk about. We have series and parallel. And then we also have a couple of different kinds of ways the water goes out of a wastewater lagoon system. So that's how the water gets into it. Where's the water go when it leaves the wastewater lagoon system? And in some cases, with total evaporation lagoons, it doesn't go anywhere, at least anywhere that you see. Some lagoon systems, you see these in Oklahoma, sometimes in Texas, very warm climates where the intent is not to discharge. It's just a holding basin. The water goes in and the water evaporates into the dry climate. These are generally very low flow facilities and they tend to have ginormous surface areas. For the most part, we don't see that many of these wastewater lagoon systems. They tend to be in incredibly small communities and there's essentially nothing in them. They just hang out of the water, let it evaporate, and then say someday in 30 years, we'll go out there with a bulldozer and pull whatever's left in the lagoon system out. Again, we don't see very many of these. The other types of wastewater facilities do have a discharge, do have an out, where the water goes when the water's done with the process. Most of what we see, I'd say more than 2/3, perhaps 3/4 of the lagoon systems are continuous discharge, which means they're discharging 24/7. The water's coming in 24/7 and the water's going out 24/7. It's a continuous plug flow process where the water's moving through at a pretty consistent rate. This is the most common facility, I think, because it maximizes the amount of treatment you can get in a given space, which is why, again, it's most common. If this is discharging all the time, the controlled discharge is discharging some of the time. We're controlling when we release the water when we want to. Generally, the discharge is done for some certain kind of ideal condition. The most common of which is we will discharge to a river or stream at a certain time of the year when we know that river or stream is high and our limits are higher in that stream. And when the summer, we'll say late summer months come around, the stream starts to dry up, the amount of water moving through is less, which means there's less dilution for the water that we're putting into it. And generally regulators will put more strict or stringent limits when the flows are lower. So some facilities will say, hey, we're gonna hang on to the water until a good time to discharge into that receiving river or stream. And the same applies with irrigation. You don't want to irrigate in the middle of winter. You're going to have big ice sculptures out in the middle of the field, especially in northern climates. So a lot of municipalities will hang on to the water and will discharge during the irrigation or growing season. What's kind of interesting actually is this photo right here. This is in Illinois. This wastewater facility has 3 treatment cells and this giant storage cell. And that giant storage cell is used to discharge onto the nearby golf course. It's an Arnold Palmer golf course. It is disinfected appropriately, and the water coming out of those heads in the morning is treated wastewater, which I think is pretty neat. The big thing with controlled discharge is you need a lot more land, and there is substantial storage required. We have to hang on to that water for 60, 180, potentially even more days of the year until the time is right for discharge. And there's a few different ways that we can discharge. I mentioned a few on the last slide. Most commonly, we see direct discharge. You just have a pipe coming out into a stream or river that will eventually end up in a lake, bay, ocean downstream. There are other types of discharge, though. There is wetland percolation, where a lagoon or a wastewater treatment plant will discharge to a wetland. This is essentially a marshy field where the water is put out. There's often trees growing in it and lots of other vegetation, and that water eventually percolates down through the water, working its way down through the earth, working its way through the many different layers of the earth, eventually getting clean before it gets to an aquifer. There's also designed versions of these, like rapid infiltration basins, and the principle is the same. We put it out into a large field or area of land, and the water percolates down through. There's also irrigation. This is somewhat similar, but instead of a marshy, pooly area, we might have a field of crops that we're growing generally for animal feed. I don't think you can do this for human consumption, where the wastewater is held for a while and then irrigated out over crops. This will provide some nutrient uptake and will potentially yield some crops that are a source of revenue moving forward. And then there's a essentially non-discharge option where it is your wastewater lagoon or your treatment facility is essentially pre-treatment. We're trying to take the edge off water. Let's say we see this more in industrial plants where their influent wastewater might be 1,000 milligrams a liter and they're paying BOD and they're paying way too much money to treat it. They'll say, hey, let's design a lagoon system that knocks the BOD from 1,000 down to 200, and then we'll discharge that 200 to a conventional treatment plant. It might be a lagoon downstream. It might be a activated sludge plant for the municipality. And what towns choose here really depends on a few different things. First of all, the time of the year that they want to discharge, the time of the year that they have permits. They might have fluctuating permits in different seasons, and what the climate is in that given area. If the climate is frozen tundra all the time, doesn't really make sense to do irrigation, for example, or even potentially wetlands, because you might end up with a field of ice instead of a field of percolating water. It also may be dependent on the size of the river or stream, or even presence of a river or stream. If there's not one nearby, or it's just a trickle, or there's endangered species in that river or stream, direct discharge might not be an option, and the wetland percolation or irrigation might make more sense for that particular municipality. I've also seen municipalities that are right on a river or stream decide to pump the wastewater to a larger river or stream 5 miles away, because there's much more water moving through that larger river, and the limits given to them by the state regulating authorities are significantly more lax in that larger river. It's actually more cost effective for that town to pump the water that 5 miles than to discharge to the neighboring stream. Okay, so let's talk about flow regime. I mentioned this earlier. The two main ones that we see with wastewater lagoon systems are series and parallel. So what do I mean by that? Let's say this is your average lagoon system here. We have 2 cells, and this can be operated in 2 different ways. I'll talk about series first. Series means the water comes in, you put it into one lagoon. This is your influent. We'll say it comes in right here, and then we transfer it when the water's done being treated in this cell. Let's say I'm going to make up an HRT, hydraulic retention time. Let's say the water sits here for 8 days. At the end of those 8 days, the water is then transferred through just continuous gravity flow into this next cell, and then sits here for, given that it's equivalently sized, we'll say 8 days, and then the water is then transferred to the effluent. This is series flow. This system is the best for treatment, and that's because it minimizes short circuiting, and you'll learn more about that in a minute. We see most wastewater lagoon systems designed this way, and you might have a 3rd cell, a 4th cell, a 5th cell. There's really no limit to how many cells you can add. But the point is, it starts in one location and moves through all of the cells. By comparison, there's another flow regime that's called parallel flow, and that's operated by taking the influent, and it is split evenly, 50-50 for each cell, and it could be 33, 33, 33 if you had a 3rd cell. The idea is it's split evenly, and then you have 2 separate treatment trains, and it could go to one cell, and these trains could be in series. There could be a combination where it's parallel flow to begin with, and then series flow in 2 different trains thereafter. But generally, we see just one train in, one lagoon in parallel flow operation. And then the effluent, for the 50% effluent from each of these is combined to create one 100% effluent that goes out. Most lagoon systems are evaluated during the design phase with a hydraulic profile, and this is because we want to maintain the plug flow operation and the gravity flow operation. We want the water to move in one direction at all times. And water, we all know, water flows downhill. It follows the path of least resistance. So when the water comes in from either the force main or through gravity flow from the collection system, we want that to be that first basin to be the highest point. And then the engineer, what they're going to do is take a look at all the different components that the water has to go through, calculate the head loss of each, and you'll notice that as the water moves through each component, and this right here, the symbol that my mouse is on, that's the water level indicator. So at the headworks, it starts at 535, and at the end of headworks, it ends at 533 feet of elevation. So that's actually quite a bit. That's a little less than 3 feet of head loss through the headworks. That's quite a bit. And then you'll see they try to minimize the head loss as the water moves through the different cells. So it moves from 533.7 or 532.79 to 532. So transferring from the end of the headworks to the beginning of this first cell, which is called pond 3. The cells are named backwards. There's a 0.79 foot head loss as you go across the continuum. Doing this math is extremely important all the way across because A, we need to make sure that if we're trying to move water to the next phase, that the head loss at that point or the water level at that point is lower than the water level here. If this lagoon was higher than this lagoon, water is not going to flow this direction, water is going to flow this direction, and we don't want that. At the same time, we want to minimize the head loss across each transfer structure because if we had, let's say this pipe was 24 inches and we made this pipe 8 inches and the head loss was huge, the water had a hard time getting from this cell to this cell. It means water is going to kind of pile up right here and not make it to this cell, and this water level will be lower. In that case, each subsequent cell is going to be lower and lower and lower and lower, and either lagoons are going to have to get deeper and deeper and deeper to have any level of volume whatsoever, or you're going to lose treatment volume. And that just seems like a waste of money. So designing in low head loss transfer structures is important to maximize the depth of each subsequent lagoon across the continuum. And this hydraulic profile is done from the lagoons through chlorine contact, through contact or effluent irrigation pump stations, other chambers as you go out the back end. But the point being, the water level starts high and ends up low at the end at discharge. Another basic that we want to evaluate here or understand is EQ or equalization. So what is equalization? Equalization is used for municipalities and especially industrial plants that have unstable flows. These flows might be unstable because the loading is all over the place. It might be 1,000 milligrams a liter one day of BOD and 20 milligrams a liter of BOD another day. That flow does have an average. It might be 350 milligrams a liter, I'm making that up. But that's not what the plant sees every day if the flow is unstable. It's getting 50 milligrams a liter one day and 1,000 milligrams a liter another day. And if we know anything about bacteria, we know bacteria prefer consistency and they can't adapt and react to really high variable loading like that. And by the same token, they can't adapt and react to really inconsistent flows. If we are getting 200,000 gallons a day one day and 20,000 gallons a day another day, the bacteria can't grow and adapt to be optimized to treat at that flow and loading level. So what we do is we design an EQ lagoon. And what this EQ lagoon does is the first lagoon in a wastewater treatment process. Water comes in, and then you have an EQ basin. And the point of that basin is to do exactly what you're seeing here, is to fill and lower as the variable flows come in. And it acts as somewhat of a tempering lagoon or kind of a battery, where out of this EQ basin, even though we have unstable flows and loads coming in, we can have stable flows coming out. We can have the average loading coming out because the loading's coming in, it's becoming one big average over a couple of days in this lagoon system and coming out at a more consistent flow. It's been tempered, and flows are tempered as well. The average, we can have inconsistent flow coming in and the average flow coming out. Overall, EQ basins are great for facilities that have, like I said, really variable loads, inconsistent flows, or high I&I, and it allows for a more optimized and cost-effective treatment at the wastewater lagoon system or other wastewater treatment process. Let's talk about freeboard and storage and the different components of a wastewater lagoon. Lagoon is not, like I said, just a big bucket that has water in it. There are different areas of that bucket or areas of that lagoon that are designed to do different things. So let's start at the bottom. You have a lagoon here, got a berm, and this is the bottom of the lagoon, and this is just representative of the different kinds of things we may design in to a wastewater lagoon. First, oftentimes engineers are going to design in a sludge accumulation zone. Sludge is it's an inevitability, really. Sludge will build up. There are ways to fix that, and we'll talk about that later. But ultimately there will be an accumulation of sludge. Most lagoons will design in, or lagoon designers will design in a foot, sometimes 2 feet of accumulated sludge storage at the bottom. And then they'll design a primary treatment zone. This is the water that, this isn't water down here, is going to be eventually sludge, so we're not going to count on that. This is the area or the volume of the pond we're going to reserve for liquid treatment. Whether it's facultative or aerated, we know that the waste will be reduced in this zone at a specific rate. And then there might be a temporary storage zone where essentially, instead of an EQ basin, some operators will use their lagoon to have a little bit of EQ built into it, which means the water level can lower and rise based on different conditions. Maybe they want to operate it differently. Maybe this accepts fluctuations in flow from the town. Could be the 8 a.m. shower time period, brings lots of water, but in the middle of the night, the water level slowly trickles down as there's less influence or inflow into the lagoon system. Most lagoons don't have that variability, but engineers do design in, on occasion, some level of variability to a lagoon side profile. And then what we have after that is what we call freeboard. This design right here only recognizes freeboard as 1 foot. I consider all of this freeboard. And what freeboard is it is extra area just in case. It is just in case we get a heavy rainfall. It is just in case we get a 24, 25 year, sometimes 50 or 100 year storm surge, and water and a lot of INI flows through the pipe and starts to fill up the lagoon. And then the top is just conservatism. We want to make sure we're never wrong. So oftentimes we'll throw another foot on top of that. Why is that important? It's pretty obvious. We don't want the water to go over the berm, because the most important part of that is if water goes over the berm, it can erode the berm side and actually destabilize the berm itself, and the lagoon can be breached essentially. So a little bit of water going out bad. All of the water in the lagoon system is catastrophic. The other reason we have a berm is we want to protect the environment. We don't want to pollute. We don't want sewage water to flow over the berm and into river, stream, playground, whatever you have next door. That being said, this area right here, we can wait for a rainfall or storm surge. Sometimes operators will use this tactically or strategically, provided that their regulators allow them to do that. Not every state will allow operators to operate within their freeboard. Some do under certain conditions. So maybe a operator is taking a lagoon offline for maintenance. They might fill up a preceding lagoon an extra couple of feet to deal or to gain some additional treatment volume, provided the regulators are okay with that. And there's a plan for what will be done with the water should there be a 25-year storm, for example. That can be done, but this is a very important thing. No matter what, you cannot have a condition under which that berm or that water overflows over the berm. So let's get a little bit deeper here. Why do hydraulics matter? Well, like I said, there's the obvious. We don't want water to go over the berm and to flood a school next door. Fun fact, this is an AI image, and the guy doesn't really have fingers or a face, but it kind of represents, hey, it looks like the berm was overtopped and water's flowing out into the stream. This is the obvious reason, but this is not why hydraulics matter. This is not why we're all here talking about this today. The reason we're here talking today, hydraulics matter because wastewater treatment is about time. How long are we hanging on to the water, and what is the water doing while we're hanging on to it? And this is where we get into one of our most critical concepts here, and that's hydraulic retention time. This is important because if you take a step back and look at what we're doing here, we're not treating the wastewater. The bacteria that are in the wastewater are treating the wastewater. All we're doing is giving them the conditions they need to treat the wastewater effectively and predictably. And what they need is food, so they can eat. They need air, so they can respirate or breathe, just like we respirate or breathe. And if we give them these bacteria under different temperature conditions will act predictably. There's a rate at which they eat, and we can calculate that and build that into our lagoon design. So we have a biological efficiency equation on the left, and what we know is how efficient any given wastewater cell is. And this is an individual cell, not the plant as a whole, is relative to the kinetic rate, K, which is how fast are the bacteria eating. Are they eating slow or are they eating fast? And they eat faster in the summer because it's warmer, and they eat slower in the winter because it's colder. And the kinetic rate's relationship with time. And if you run this calculation for any wastewater lagoon, what you'll find is that as time increases, the amount of food that gets eaten in that given cell increases with it. So in one day, in one cell, 71% of the food can be eaten. But if you go to 10 days, across those 10 days, 96% of the food can be eaten. So the point here with hydraulic retention time is the longer we hold on to water, the more the bacteria in that water are going to eat the waste that we don't want in the water. This is the whole point of wastewater treatment, right? We want clean, non-polluting water out the back end of the plant, so we're not harming rivers, streams, fields, that sort of thing. So if you take a look over here on the right, this is how this equation works out with a typical wastewater plant. We'll say a 3-cell lagoon system. And there's a difference here. This is 1 cell, this is multi-cell. And the difference is, this is the efficiency per cell. So we can treat 70, if we have 3 one-day cells in a row, we can treat 71% of the waste in the first cell, and then 71% of the waste that goes into the next cell. We can treat 71% of that, and then 71% of the waste that goes into the third cell gets treated in that third cell. It's kind of complicated, but there's essentially diminishing returns as you go down the continuum. That's why you see this curve taper off. System-wide, this is how it tends to unfold. In the winter, we see treatment that's a little bit lower in the summer, but they track roughly the same line. That the majority of the treatment, 10 to 70%, 60 to 70% happens in the first 10 days, and we can get around 90% treatment with 50 days of detention. This could be augmented or changed, but it gives you a sense where most of the treatment happens up front when we hold on to it for the first third of treatment. And then when we're discharging, most plants will discharge around 30 days. We can treat 80 to 90% of the waste in that system. So how do we calculate HRT? HRT is what I'm going to be using as an acronym for hydraulic retention time. It's very simple. It's a function of what is, well, first of all, I guess, what are you looking at? You're looking at the HRT of your entire lagoon system, or are you looking at a HRT of an individual cell? For this example, we're looking at the HRT of an entire lagoon system. So this might be multiple cells together. So HRT is the millions of gallons of lagoon volume divided by the millions of gallons per day of lagoon flow. So for example, let's say we have multiple lagoons and they total 7.4 million gallons. And we have a flow coming into those lagoons, or at least a design flow. It could be variable, but we'll calculate this at a max. A max daily flow of 0.24 million gallons per day. All you gotta do is take 7.4 divided by 0.24. And then what we find out is, in this sample case, the HRT of the lagoon system is 30.83 days. And this is a physical limit. We can't make these lagoon systems hold any more than that 30.83 days, unless you want to get out there and dig lagoons deeper and reline them or burn them up. And that is unbelievably expensive. And I rarely see that outside of some industrial cowboy operations. So if we consider this a functional limit and we're not going to mess with the volume of the lagoon system, the question is, how do we optimize this infrastructure that we have to maximize its treatment potential? If it's not optimized, then we're not utilizing the full volume, the full HRT for treatment. So what are the drivers of HRT, or hydraulic retention time? Why do we need more hydraulic retention time in some cases than in others? And that is what's coming in, how fast can we treat it, what do we need going out, and storage requirements. So what's coming in? If flow increases, it's going to bring more loading with it. We may need to hold on to the water longer. Biological oxygen demand, if more BOD, more carbon comes into the plant, if you have 1,000 BOD coming in versus 100 milligrams a liter BOD, we're going to need more HRT to treat that water down to some effluent limit point. And same with NBOD or ammonia. It also comes down to how fast we can treat it. The design temperature has you saw earlier, for example, between winter and summer, there is a difference in design temperature and HRT. If the water is colder, the water will be treated at a slower rate because the bacteria move slower. And in that case, we will need more HRT to accommodate for those colder temperatures. Also, we can augment the kinetic rate. So if that K that I discussed earlier, we can increase that K rate by increasing the mixing we put in the lagoon system. If we get the bacteria, the waste, and the air more in contact with each other, we can get them to eat the waste faster than a typical partial mixed lagoon system would do. Point being, if we increase the mix rate, we can decrease the HRT, or how long we need to hold on to the water, because we're eating it at a faster rate. What do we need going out of the plant? If the effluent limit is 80 milligrams a liter of BOD, that's an easier number to get to. We don't have to hold on to the waste as long to get to that number than if we are trying to get to a effluent limit of 10 milligrams a liter. We might have to hold on to the water an extra 10 or 15 days to get it from 80 milligrams a liter down to that 15 effluent limit. And then there's also storage requirements. In some cases, lagoon systems will have a controlled discharge lagoon where they want to store water until a certain point, or equalization. We want hydraulic retention time simply for storage or EQ. And it's a really interesting interplay too. So what we have is a chart here showing flow on this axis and volume on this axis. And the question this chart answers is, how much BOD can be treated in a lagoon at these two conditions down to 30 milligrams a liter? So if you have a 1 million gallon a day, or sorry, 1 million gallon lagoon, really little lagoon, and you have 100,000 gallons per day, you can treat 150 BOD down to 30 milligrams a liter. But as you increase flow, you can treat less and less BOD in that lagoon system. If you have a 1 million gallon lagoon system at a 1 million gallon per day flow, that's a 1-day HRT. So we're only able to treat 40 milligrams a liter down to 30 milligrams a liter. We're only knocking off 10 milligrams a liter in that 1 day. There's not a lot of treatment happening in that lagoon system. As a flip side, if we have that 100,000 gallon per day system, and if we are working with a cell that's 1 million gallons per day, or sorry, 1 million gallons, we can only treat 150 milligrams a liter. But as you increase the volume, or you could see this as increasing HRT, hydraulic retention time, you increase HRT, you can treat more and more, a crazy amount of BOD in a small space if you're hanging on to it for a longer time. And this just shows simply the power of bacteria and time in HRT. I mentioned earlier that kinetic rates, there's a few different kinetic rates that we can use. Most lagoon systems are designed as this green line, a partial mix, but you can go all the way up to complete mix by providing more mixing energy into the lagoon system in the same space. This would reduce HRT requirements. It allows you to treat the wastewater much faster. But you can see, compared to facultative, the amount of time that the lagoon needs to treat the wastewater is significantly more. Facultative lagoon systems with no aeration and no treatment other than natural sources in 30 days are only going to remove about 38% of the wastes that are in them. You compare that to a partial mix system with a little bit of aeration, it can remove 80% in 30 days. And you move up to the complete mix system. This is the high treatment rate process. Most lagoon systems aren't designed here, but they can be. In those 30 days, we can remove 98% of the waste. So it's all about how long we hang on to it and how fast the bacteria are moving with the kinetic rate. And there are some threats to hydraulic retention time. If HRT is what essentially drives the size and treatment in a lagoon system, what are the threats? And the most common ones are short circuiting, where we are, we'll explain what short circuiting is in a second, but that's usually due to little or no aeration or mixing, poor pond design, sludge accumulation and channeling, stratification, I&I. There are some other threats. The operator operating a lagoon system outside of its design point, that doesn't happen too often, but it is worth talking about. So let's get into the meat of it. What is short circuiting? Short circuiting is when the water isn't held onto as long as the lagoon was designed to hold on to the water. What that means is the water's coming in on one side of the lagoon system. Instead of hanging out in here for, we'll say, 10 days of HRT, the water's just beelining it for the exit. So if we're trying to hang on to the water for 10 days, kind of keep it slow and steady, the water's leaving maybe in 3 days. It's moving too fast. And that means the water's never even touching these areas of the pond system. It's short circuiting from the influent to the effluent. And in this case, we're actually only getting a 3-day HRT on the water that's moving through here. We're not getting the full 10-day HRT utilization. And the water does essentially what people do. it is, you know, we could have designers that say, hey, people should walk on this tortured path right here, but people don't want to do that. They're going to take the path of least resistance and cut straight to the point. That's exactly what the water is going to do too. So what we want to do is design the lagoon to such that the water moves the way that we want the water to move, and or to put things in the lagoon to make sure the water moves the way that we want it to do. So we're going to be talking about a whole bunch of different things here regarding short circuiting. We got Johnny Five making a 1980s joke. I might make another one later. The main things we want to do to avoid short circuiting is know the patterns in the lagoon system. We want to trace where the water's going. We want to have a lagoon that has the right shape. We want to have a lagoon that has mixing. The design of the influent and effluent location is very, very important, and what those influent and effluents look like can be augmented to avoid short circuiting. Sludge management is also important. You can also recirculate to avoid some short circuiting. So there's a few ways that you can test for short circuiting. I think the best and easiest is using dye tracing, although this does cost some money. And what you'll see here is we had a lagoon system. We want to do an evaluation. We put some dye in the influent structure, and you'll see it pop up right here first, and then it go out the effluent pipe right here that you see. We thought the influent of this lagoon system was right here, but there were no as-builts. And when we finally did the test, you'll see that the influent is all of 25 feet away from the effluent. So we learned very quickly that the dye shoots up here and shoots right for the effluent, and we diagnose an issue pretty quickly with dye tracing. You can also get dye with rhodamine in it. Essentially, it's a chemical compound that can be detected to extremely low levels. So it can be put in at the influent and then tested with a sensor on the effluent to find out what concentrations of dye are showing up and over what intervals. And they'll give you a sense of what short circuiting, how much, and when. You can use CFD to test short circuiting. This is a very expensive way of doing it, where you plug in the different lagoon design parameters into a computer program, and it can tell you how much HRT or how long the water has been sitting at different areas. So you see blue, it's pretty fresh water up to about 50 days. The blue water kind of spills over here and turns yellow. It's the middle range, and then the scaling goes up to red on the far side. You'll see that this is a great way to detect dead zones. This whole lagoon is supposed to only have a 30 or 50-day HRT, I believe. And there are some red areas right here that develop. You can see right here and right here, where the water is essentially not moving. It's got a 100-day plus HRT. And it would be very difficult to figure out where the dead zones in this lagoon without CFD. I would say this is a level of analysis that's not really necessary for most lagoon systems, especially municipal, but this is an option to those available if they were interested. I think one of the simplest and quickest ways, without going and spending a couple $1,000s on rhodium or dye tracing, is using what we call a drogue. And you might know drogues from sailing or from fishing, but the idea is putting something in the water that sits low in the water and moves with the water, and something that we can track. You can buy expensive geologic survey materials, drones that are crazy. I don't recommend you do that. They can be very, very expensive. You can use something as simple as an orange. So I got a photo here, some oranges in water. And oranges are great because they're mostly liquid on the inside. Their specific gravity is close to 1, so they don't float a lot, they don't sink a lot. They sit just in the water, such that they stay at the surface and you can see them. And if you think this is silly, I mean, I've got a bit of a side story here. This came from Steve Harris, if you're familiar with him, with H&S Environmental. Great guy. We learned a lot of these things from Steve. He was talking to one of his customers, these are his photos, about doing dye testing because his lagoon was not operating the way that he originally intended. And the operator's like, $3,000 for dye? Screw that, I'm not gonna do that. He went down the street, went to the market, bought a basket full of oranges and tossed them in his influent structure. You can see them coming out right here. And if the lagoon was operating as designed, these should have turned and gone this direction right here and gone towards the effluent. And that's not what they did. They actually went straight and they skirted along the outside very quickly, moved over here and ended up within a matter of 24 or 48 hours right by the effluent. So what this showed the operator is that there's a flow or a current moving around all the aeration, around where the treatment is supposed to be happening, and beelining it for the effluent in 2 days, 1 or 2 days, instead of it hanging out in this lagoon system for perhaps the design 10 or 20 days. So that gave the operator a clue that he needs to disrupt this channel right here to prevent the flow doing what it's doing in this lagoon. Most lagoons are rectangular. That's because they're very easy to construct. Kind of hard to construct a constant berm or slope rather if you had a circular pond. And they're also easier to control. It's easy to put transfer structures in between rectangular cells. They maximize the volume given their space. It's easy to throw a baffle in. And they're also rectangular because we want to create a physical space between where the influent might be and where the effluent might be. And we want, again, to control the water as it moves through the process. You can get some pretty extreme examples of that. These are some hairpin lagoons where the water comes in on one side, has to go all the way down, make a turn, and come all the way back. You don't see this sort of thing except for primarily in industrial cases where there's a huge loading, and we really, really need to control HRT to get the treatment that's anticipated. So let's talk about mixing. Why do we need it? We need mixing in lagoon systems because the lagoon itself is not homogeneous. What happens is, as the water sits, it'll separate into distinct layers separated by what's called a thermocline. You get colder, denser water at the bottom, warmer, lighter water at the top. And the thermocline in between them is actually a physical barrier. These two waters don't mix well. They don't want to mix. And that's why we need to, oftentimes in lagoons, add additional mixing to make sure we don't get this, what we call thermal stratification. And the reason this is important is what happens is you have warm influent coming in, and that warm influent is lighter because warmer water is a little bit less dense. The water comes in and it comes in contact with this colder, denser water. And it's going to be buoyant in that water, and it'll actually float up and move up into this upper, warmer, lighter water layer. That means we're not utilizing the full volume for treatment. The influence going up and hanging out just in this upper layer, so we're not maximizing treatment. And that means the water is moving faster in this layer, given the overall volume, and will beeline it or short circuit to the exit more quickly. This will result in influent water making it to the effluent, raising fecal counts, raising BOD. There is some mixing that occurs naturally in the lagoon system with wind and rain or seasonal turnover, but usually what we want to do is add some level of supplemental mixing with diffused aeration or surface aeration. And oftentimes, we get asked, like, what the heck happened to my lagoon? It was a milky green, it was a good color, it was healthy, it didn't have any odor. One day, I came in the next day, it's black, there's popping sludge, there's bubbles coming up, it stinks. What happened? And what you're seeing is essentially natural mixing or pond turnover. And this happens in most lagoon systems that are not mixed, and it'll happen about twice a year. And what happens is you use two separate layers, as we talked about earlier, and when these layers flip, invert, or mix under certain conditions. So down here, we have a layer that doesn't have a lot of oxygen if it's not a well-mixed lagoon. So it's going to have low DO, it doesn't have any oxygen transfer from the surface or the wind, and it's separated by this physical barrier. And then we have a lot of anaerobic digestion down here. And the anaerobic digestion is going to produce H2S, methane. It's going to have benthal feedback of phosphorus and ammonia. And all of that it's releasing stays in this layer because it's stuck by this persistent barrier. Eventually, these can mix under certain conditions. And all of this that's been building up over a period of time gets mixed with the upper layer. And that's why the operator who's saying, what the heck happened to my lagoon? They are seeing all of these toxic, low DO, odorous things coming from the bottom of the lagoon and presenting at the top. It was out of sight, out of mind before that. And turnover happens because those layers mix. What happens is you get stratification in the warmer months, but as the water cools, and especially in northern climates, this water up here is exposed to wind and cooling. It cools down. It can cool down to the point where it's actually colder than the water beneath it, causing it to be more dense, and that water will fall and mix and push all of that toxic, high BOD, high ammonia water to the surface. And that when that mixing occurs, it will challenge the lagoon system, DO drops, and oftentimes fecal and BOD and ammonia content will raise in the effluent. And the same thing happens in the spring, especially in northern climates when you have ice melt or potentially a strong rain where lots of cold water is dumped on the surface. That dense water will then sink, pushing the bottom stuff up to the surface, creating pond turnover. So what we want to do, I think the best case scenario is if you can mix those layers up continuously, you don't have pond turnover, you don't have this BOD and fecal matter, high E. coli rather in the effluent, because we're mixing it all the time. So you can do that with diffused aeration. Right here is a diffused aerator put in the bottom of the lagoon system. When this animation starts, you can see all the water is blue, and blue is essentially low velocity, not really moving around. And as we add air and mixing into the lagoon, the entire basin, there's blue here, the entire basin starts to move around. You see eddies created, you see water moving, and this force or this movement will de-stratify the pond such that these layers cannot form, or if you're lightly aerating the pond, they don't form as intensely as they would otherwise, and it minimizes the impact of pond turnover. But a well-mixed, partial mixed lagoon should not see pond turnover if they are aerated like this. It can be done a couple of different ways. What I just showed you was diffused aeration, so releasing bubbles from the bottom to the top. This type of aeration doesn't really matter how deep it is. The aerator is generally on the bottom, and the bubbles rise as they should because they're buoyant all the way to the surface. So that mixing energy is brought all the way to the surface. Another feature of subsurface or diffused aeration is that generally diffused aeration systems have more points of energy release, and then therefore they're mixing more points of the pond. One alternative is surface aeration. This is a little bit less expensive to install. We'll say it's more cost effective to install. But in general, surface aerated facilities have fewer points of energy distribution, where they might have 30 aerators in the bottom of the pond. They might only have 5 or 10 surface aerators on the top of the pond. So there's less mixing points throughout the basin, and it's also mixing from the top to the bottom. So what you're seeing is tons of turbulence and mixing right at the surface. But if we were to make, let's say this is 5 feet deep, if we were to make this 15 feet deep, getting the mixing energy to the bottom is more difficult. So surface aeration is not as effective at mixing the layers as the pond depth is increased. Stratification can happen at lower depths. One thing we can do to minimize short circuiting is pay attention to the influent and effluent locations. So if we were to put influent here and an effluent there, that'd be really dumb because the water is just going to go out one pipe and into the other. We can say, okay, we'll move them apart. The water's going to come in, go all the way down here, and go down the effluent, right? Well, no. If you remember, water is going to follow the path of least resistance, and it's going to go like this. And the HRT, this whole lagoon might have an HRD of 40 days, and the water's making it out in 5. So the whole idea is we want to keep them separated. We want the influent to be as far from the effluent as we can get it, and we want to alternate as we go down the lagoon system. So we're maximizing the distance the water has to travel, so we're maximizing utilization in the lagoon system. The water has to take this longer path to get out to the effluent. And that means we're maximizing the HRT. We're hanging onto the water as long as we can to get the treatment that we want to get. We can make this even better by adjusting how the influent manifold is made. Because what happens is we have an influent manifold and water will create a channel. You can't see it, but it'll create a bit of a river where the water might be moving at a faster rate through the basin than the HRT design would suggest. This is especially bad if you have a force main that shoots directly into the basin, because that force main is ejecting water at 5 to 8 feet per second into the basin, or shooting it and encouraging this channeling to happen. So what we can do is design an influent manifold where the waste comes in and then is diffused through multiple different outlet points. So in this case, we're spreading out the influent, and that because we're spreading out the flow, we're decreasing the speed of that flow out of the influent. And then it also creates competing flow zones where this channeling has to compete with this channeling, and that turbulence creates mixing, and that mixing holds the water back. Creating an influent manifold like this will increase the effective HRT in your lagoon system and minimize channeling. We recommend 3 up to 5 pipes. Kind of past that point, you do get decreasing benefits and just a increased complexity of influent pipe. Another thing to consider about is a effluent manifold. And if the influent manifold was horizontal, we want the effluent manifold to be vertical, or to be at different levels at the back end of the pond. And that's because lagoons are often stratified. The water at the bottom of the pond is going to be different than the water at the top of the pond, unless it's very well mixed. We've got to be careful. We don't want to put a draw-off point at the very top and the very bottom, because the top, we're going to be skimming off the surface of the water. Solids will be algae and other debris, sticks, whatnot, are going to be drawn off, and it's going to end up eventually in your sample bottle. This is not a good spot to draw off. And same with sludge at the bottom. We don't want to be pulling old digested sludge off into the effluent, because that will show up and potentially help make you breach effluent limits. So usually we recommend 3 or 4 draw-off points at varying levels. And what the operator can do is at different points of the year, depending on how the aeration is utilized, how the flow and load patterns are at different points of the year, the water will be different at different depths. The operator can choose, or actually take a draw off at each level, do a sample, get a sense of where the water is best at that point, and utilize each draw-off point when it's the best fit. Baffles are also very, very good in wastewater lagoons to prevent short circuiting. Again, we're back to how do we stop the water from beelining it from the influent to the effluent, and we're holding the water and the loading back so it can treat as we expected. So what baffles do is they create a tortured path. And this essentially emulates creating additional cells. We can create virtual cells in a lagoon system simply by adding a baffle. Every single time you add a baffle, you'll increase the treatment efficiency of your lagoon system, which means you're increasing the treatment capacity in the infrastructure you already have. It's a pretty powerful thing. So this is a chart showing if we have a static lagoon, it is, do we have a volume here? Yeah, we have a treatment time of, do we have a volume? Do not have a volume, but we'll say the volume is held steady here, the flow is held steady, and at 0.2 mgd, and the influent is held steady at 200 milligrams a liter. What is the effluent BOD if we add additional cells with additional baffles? So if we have one cell, we can treat in this flow and loading condition down to 46 milligrams a liter in the winter. If we add a baffle, we can, that just by adding the baffle, we can, that same volume can treat down to 28 milligrams a liter. We add 2 baffles, or we create 4 cells rather, so that's 3 baffles. We can treat down to 18 milligrams a liter. And this is getting a little bit crazy. We don't recommend going up to 6 cells, but with additional baffles, we can treat down to 14 milligrams a liter. Again, the point here is what we don't have is raw influent short circuiting as frequently to the effluent, and that means the effluent, we're seeing lower and lower treatment values. And this applies not just to BOD, this is fecal coliform as well. You'll see this is a lagoon system from a study from Schulten and Harrison, and the fecal coliform in the effluent was extremely high in this one case in an unbaffled lagoon. And simply by adding baffles, any baffles at all, there's a big difference between 2 and 6, but the biggest difference is by adding any bafflage at all, is that the raw influent waste is not making it to the effluent in time, and therefore the fecal count is going down. From an optimization standpoint, we recommend a minimum of 2. That's usually the best number. That will maximize the amount of back and forth the water has to do. And the best baffle design that we have found is doing a 70% baffle. 70% of the lagoon width is covered, leaving a 30%, this drawing is not to scale, leaving a 30% gap. And that's because the water can move very slowly all the way around. Some baffles will have a window instead. What the window does is it kind of concentrates the flow a little bit. It's kind of like squeezing a hose. You know, water's coming out at a slow speed, but if you concentrate that flow by squeezing it, water comes out faster, creates a bit of a jet. And in that case, that jetting of windowed baffles can create quicker flow. This doesn't mean that we don't use window baffles, we absolutely do, but it's important to work with the baffle manufacturer to size the windows such that the water flow going through it is kept below a certain level. And the baffle manufacturers can work with that, but don't just buy any baffle off the shelf and throw it in, because that window might be actually making your problem worse. A couple of things to note here. Looks like we're going to go a little bit over on time. I will move a little bit quicker. Is that elevation air pressure do apply to hydraulics. Air is a fluid, and the air changes. Stratification happens in the atmosphere, just like stratification happens in water columns. So if you go higher up at elevation, there's less air pressure, there is less air density, and therefore there's less oxygen in the air. The oxygen up in Denver might be 19% or 20%, where the oxygen down at sea level is 21 or 22%, simply because the air is less dense in Denver. So if you have a blower at a lagoon system, it takes more blower rotations to move more of the less dense air to get the same O2 demand met in a lagoon system. So just note that with elevation and air pressure changes, you will get a difference in airflow. This is a conversation for a different webinar, but something worth keeping in mind while we're talking about hydraulics. And temperature also has a lot of overlap with hydraulics. Again, Steve Harris, big expert. He's all about measuring temperature in lagoons. He thinks it's a really great predictor of water quality. It's a great operational tool for evaluating changes in pond performance. So, for example, if you're seeing rapid changes in temperature, this can indicate pond turnover or treatment performance changes. And temperature interacts with a lot of different things. It does interact with pond turnover or pond stratification. It can encourage or discourage that thermocline formation. Temperature will also increase or decrease HRT needs. As you saw, winter and summer elicits different treatment efficiency values from the treatment efficiency calculation. So basically bacteria eat faster and need less HRT when it's warmer than they do when it's cold. Higher temperatures can reduce DO. It can reduce phosphorus removal, or increase phosphorus removal. It can decrease sludge accumulation if it's warmer, and it can slow down nitrification. Temperature will change the kinetic rate of what's going on in your lagoon system and will impact stratification in the lagoon system. So tracking it, developing patterns over what's happening in your lagoon system at different seasons, different temperature conditions, is a great tool to predict what might happen in future years. So let's talk about sludge. Sludge can actually cause short circuiting. So as we know, we have sludge at the bottom of a lagoon. And if this lagoon system, for example, is designed to have 2 feet of sludge at its max, and the operator does not remove sludge for 10, 20, 30 years, and that sludge builds up to 3 feet, 4 feet, 5 feet, that sludge is taking up space that we were otherwise designating for a different purpose. And oftentimes the water that we're taking up is the liquid treatment zone. So if we have more sludge than design, that means we have less treatment zone than design. If that treatment design zone is smaller, that means it has less HRT. If we're hanging on to the water for less time, we are going to get less treatment in that zone. Instead of, for example, the 90% treatment we were looking for, we might be only getting 70%. And that means there could be increased BOD and ammonia and TSS in the effluent, because it's decreasing the treatment volume in the lagoon system. Oftentimes, sludge removal is possible by treating the volatile organics. There are parts of the sludge that we're never going to treat. And there are ash, there might be clay down there might be grit. Bacteria are not going to break down rocks. But if you have volatile carbon organics at the bottom, those can be broken down through a variety of other methodologies. We have entire webinars in the university directly on that. But sludge can also create channeling. You know, you've seen probably rivers change from satellite views on the right based on time. This same thing happens under the water in the sludge, especially in undermixed lagoons or shallow lagoons with high sludge. The sludge can actually form subsurface rivers that will direct the wastewater or channel the wastewater, helping it to short circuit from the influent to the effluent. So something to keep in mind if you have a shallow lagoon that's not mixed with quite a bit of sludge. Recirculation is a fantastic tool hydraulically to improve the treatment in your lagoon system. And here's the quick and dirty of it. What happens is we have water coming in, moving in by series flow from one cell to the next cell to the next cell. We get BOD treatment generally at the front end of the plant, because this is where BOD is high. BOD treatment typically happens before nitrification. So this is where you get BOD treatment. The water is discharged into a third cell. Later in your treatment process is where nitrification is going to take place. This is generally when the BOD is below 20, 30, 40 milligrams a liter. Well, you start to get ammonia treatment, and that nitrification breaks ammonia down from NH3 to nitrate. And nitrate is a really interesting molecule. Right here, you can see it. It is one Nitrate is 1 molecule of nitrogen, 3 molecules of oxygen. That means there's oxygen here that's being produced in this nitrification cell as the ammonia breaks down. So if we recirculate that water back to the front end of the plant, we're bringing all this oxygen back to the front end of the plant where these heterotrophs can strip off this oxygen. And you're actually essentially bringing free DO to the front end of the plant. You're also bringing high DO water because this water is sitting out for long periods of time, lots of winds going across it, and it's low BOD as we've already discussed. Typically, you're going to see higher DOs in this cell. That higher DO water, you're bringing free DO to the front end of the plant there as well. When you're bringing water back and recirculating, people always ask, well, if I have a 0.2 mgd flow and I do a 1Q or a 0.2 mgd recycle, aren't I doubling the flow? Aren't I going to have 0.4 mgd flow at that point? No, that's not how it works. Because the water coming in is 0.2 and the water coming out is 0.2. All we're doing is creating a circular flow within the plant for some reason. In this case, we're looking for free oxygen. The water coming in here at low BOD will dilute the BOD that's coming in. So the net effect of this recirculation is no negative treatment impact. And it is a great way to get free DO. A couple of closing things here. One of the big benefits of lagoon systems is their long HRT. We're not trying to treat wastewater in 12 hours or 24 hours like a mechanical plant might do. We have longer HRT, and that's fantastic. So we're not looking at just BOD 5, how much BOD do we remove in 5 days? Lagoons have BOD 500, BOD 1000. When those solids settle out into the sludge, that sludge sits there for 10, 20, 30 years and has a very long time to break down. And what we're finding, there's a study out of Illinois that found that lagoons are the best treatment process, at least conventional treatment process, for the reduction or elimination of pharmaceuticals or personal care products, or PCCBs. So you hear about all these pharmaceuticals, medications, steroids, hormones that people are putting down their toilet or flushing down their toilet, or one way or another ending up at the wastewater treatment facility. Those high rate treatment processes can't treat it. You can't treat hormones and steroids in an activated sludge plant. But because lagoons hang on to the water so much longer, the different microbes and bacteria have a longer time to break down the proteins and different synthesized chains in those pharmaceuticals to make them inert and make them not a problem for the environment we're discharging them to. So we always like to say that someday we might have replacement of mechanical plants with lagoon systems because of the constituents they treat down to lower levels that are not practical in those mechanical plants. A couple of quick tips. This is quick. I'll go through it quick and not tell the story. We have seen in the past erratic high BOD numbers at the end of treatment plants, where you can measure all the way across the continuum. BOD is going down, 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 and that the effluent, it might be 30 milligrams a liter, 30 milligrams a liter, 30 milligrams a liter, and then 200 milligrams a liter, or some high spiky value at unpredictable points. From a hydraulic standpoint, one thing to look for is solids building up in an effluent chamber, whether it's a chlorine contact chamber or in some final effluent chamber. These solids can build up, they can go anaerobic, and occasionally get burped up and end up in the BOD bottle on the back end. So if you're getting really spiky, unpredictable, unexplainable values out of the back end of your plant, take a look at cleaning out these basins oftentimes, but that can be a way to solve that problem. And then very quickly, if you have the room in your hydraulic profile to add a waterfall at the back end, waterfalls are a great thing to add, especially if you have high DO requirements on your effluent limit. Some towns are required to have 4, 5, 6, I've seen up to 8 milligrams a liter DO on the tail end. If you have a waterfall, you take advantage of that gravity fall. Waterfalls are white because you see a lot of air in them. That's air being mixed in. So the water might be coming in at 3 DO and coming out at 6 or 8 DO. It's an inexpensive way to increase DO on the back end of your plant. So sorry for the rush at the end there. I appreciate your patience. This has been a great webinar. I think the big things that we've talked about here is, you know, that lagoon treatment requires HRT. We're holding the water back so the bacteria can do its job. And then therefore, how we design the holding back of the water, the hydraulic design of that lagoon system is absolutely important, especially minimizing short circuiting, just so we're making sure the treatment that we designed to take place does take place. So hopefully with your knowledge of lagoon hydraulics here, you can either optimize your lagoon system, your lagoon's performance, or design eventually a lagoon system that will be installed that will operate the way that you expect. So now that we're here, I'm happy to answer any questions on Lagoon hydraulics.
Brady, since we're so far over, we'll take questions either in the chat or by email or in the survey box, and we'll get back to people afterwards.
That's perfect. All right, that makes a lot of sense. Thank you very much, Eve. All right, well, that concludes our webinar for the day. Again, Module 3 on Lagoon hydraulics. It's been a great webinar. Thanks for sticking with me, and I hope you all have a fantastic day.